Hi everyone, welcome back to Math 261. This is Scott. Let's get started. What we are going to be doing now is embarking on a new adventure, Chapter 5. So we are going to be leaving behind for a little while some of the forests of abstraction that have been present with us in this part of our journey, namely Chapter 4, which got pretty deep in the weeds on matters of generalized vector spaces. And now what we're going to see more or less is what it's all good for. And the topic of Chapter 5 is all things eigen, eigenvectors, eigenvalues, eigenspaces, things like that. And so what we're going to be doing here is first making a couple of new friends. So eigenvectors and eigenvalues, and we're going to see what that means and how we can find some of these things. Eigenvectors and eigenvalues. So first just a note on the language here because it's so strange looking. So eigen anything is a prefix that means particular or characteristic. You may think it's somebody's name. It sounds like it might be a name or something, but it's not. It's just a German word. So this is a prefix that we put, and it means particular or characteristic. So in particular, an eigenvector and an eigenvalue will be particular or characteristic vectors and values that are associated with a certain matrix. Now, the matrix that we'll be talking about is always going to be assumed to be square. So setup here is that A is n by n, in other words, square. We're going to be mostly assuming square matrices for the rest of this course. There will be some exceptions, but for the most part, square matrices are where a lot of the action is. And I'll discuss why that is as we get into the details of all of this stuff. So first off, here's the definition of the terms here, eigenvectors and eigenvalues. And then we'll see how that definition can lead us down the path of actually being able to find these things. And then later we'll see how we can actually make use of these things in certain contexts. So, if x is a non-zero vector of Rn, so here Rn, I mean, is the same as the n up there. If x is a non-zero vector of Rn, and lambda is any real number, then x is an eigenvector of A with eigenvalue lambda whenever ax is equal to lambda x. All right, so let's think about this. So this is the definition. Ax equals lambda x. So A is a matrix. Lambda, however, is not. It's just a number. So what this is saying is we're looking to find a particular vector such that multiplying it by A is the same as just scaling it by lambda. So what this means geometrically, If we consider A to be a transformation, a linear transformation, so if A is the matrix of a linear transformation, remember those? Then an eigenvector of A is a vector that keeps the same direction. The same direction after applying A. So that is actually, although I've now couched it in an even more abstract formation, this is actually going to be the key to what makes it valuable. So in particular, in a later section at the end of this chapter, we'll be looking at what are called transition matrices, and we'll see what eigenvalues mean for that, and eigenvectors. And in particular, in Math 256, we're going to be looking at systems of differential equations as being, in a way, a linear transformation, and then that means that the eigenvalues and eigenvectors are going to represent some easier pieces of the linear transformation puzzle. Okay. Well, let's think about the fundamental relationship there, ax equals lambda x, and what that can lead us to as far as being able to actually find stuff. So here's our first goal. So this is separate. Now, new thing, goal. So our first goal here is, if I am just given a lambda out of thin air, then it's going to be my task to try to figure out what eigenvectors would be associated with that eigenvalue. So goal. First phase of our operations here, given an eigenvalue lambda, and lambda is the default letter that is almost universally used for eigenvalues. So given an eigenvalue lambda, find associated eigenvectors. Okay, so let's think about this. So here's the key. So taking the equation ax equals lambda x, what we are going to be looking at is basically seeing if we can't solve this for x. So we're supposing here that we know lambda, and we want to solve this for x. So let's just think about how you would do this if this were just in numbers. So if these were numbers, you would solve this equation by moving everything to one side. But they're not numbers, they're vectors. So then getting 0 over here means getting the 0 vector. But here we would want to be able to factor out the x, but we can't do that because I can't factor an x out of these two things and leave behind a subtraction, because this would not actually be defined. A minus lambda. A is a vector, or I mean A is a matrix, lambda is a number, and there's no such thing as subtracting just a number from a matrix. They have to be the same species. So here's what we can do to write this. So now I want lambda to be a matrix. So we want this to be a matrix. So we want to write this in a way compatible with A. That would allow us to factor out the x vector. Well, we can't factor it out right now. It doesn't quite make sense. But we can rewrite it like so. And this will be our default way of rewriting it. So this is a standard trick. So I can't do lambda from A, but x is the same as the identity times x, which means, so this is like a little commentary track for it's exclusive content for subscribers and Patreon patrons. So this, so here what we want is we want to rewrite it as the identity times x, and now if you look at this, this now has become something that is a matrix. Lambda times the identity is actually a matrix, and it can be then put into the same bucket as A, and in particular we can subtract it. So what this actually then really represents is a scaling of the identity matrix. And remember, the identity matrix is the one that has ones down the main diagonal. So what that means is that this is actually the matrix that just has lambdas in the main diagonal. So lambdas on main diagonal. That's what that means. So if I already know the lambda, then I can actually compute this by figuring out what A would be if I subtracted lambda off of its main diagonal at each stage. But what we're looking for is non-zero solutions to this. So we want non-trivial solutions to this equation. But wait, we have a term for that. That is the null space. So in other words, what we want is to find vectors in the null space of this matrix. So thus, we want to find a basis for the null space. Of A minus lambda I. So in other words, we want to get it so that we can actually find vectors that will produce this nullification when multiplied by this matrix, but which are not themselves trivial. So let's try this. As an example, so let's say that I am given a lambda of 3. So example, let's just say lambda equals 3. Here's a couple tasks. Step 1, A. Is lambda an eigenvalue of A, which will be equal to 2, 4, 1, -1. So that's task number 1. And the answer may be yes, it may be no. If the answer is yes, then we should be able to find an associated eigenvector. So B, or no, not B, really, follow-up. If so, I guess really, this is not going to be two parts. So if so, find an associated eigenvector. All right. Well, let's think about what this means. So first, let's just build this up. So if lambda equals 3, then lambda I would be 3's along the main diagonal, and here we're talking about 2 by 2 matrices. So then A minus lambda I would equal 2, 4, 1, -1 minus 3, 0, 0, 3, which then means we just subtract along the entry by entry fashion. So then we have -1, 4, and then we have down here 1, -4. Now, the question, is this an eigenvalue, is tantamount to saying, is there a non-trivial solution to A minus lambda I times x equals 0? And that we can answer in the affirmative, because we can see that this is not going to be, this is not going to row reduce down to a situation where we have a pivot in every column, which means our null space has got some juice to it. So what this means is, so we can easily see what's going to happen if we row reduce this. We're going to end up with zeros down here, and we're going to have like 1, -4 up here. So this has a non-trivial null space. So lambda equals 3 is an eigenvector, an eigenvalue, I mean. But now let's find the eigenvector. Okay? Eigenvector. Well, we know, so we can just basically take this pop on a couple zeros in typical row reduction fashion. And what this is going to tell us is that x1 minus 4x2 will equal 0, which means that x1 equals 4x2, and x2 is free, so that means x2 just equals x2. And then what that means is that an eigenvector here would be something where we have x2 times 4, 1. So just kind of standard parametric form. And what that means is basically 4, 1 will be an eigenvector. So it's an eigenvector of A with eigenvalue of 3. All right. What would it have looked like if what we were looking at was not an eigenvector, or an eigenvalue, I mean. So let's repeat this, but now let's change things. So another example. So let's say lambda equals 2 and a equals 1, 1, 3, 1, just for example. Okay, well, if we subtract, so we'll mostly cut to the chase on this. A minus lambda I is going to equal. So basically, if we just repeat what we did, but now with a value of 2, it's going to be a negative 1, a 1, a 3, and a negative 1. So we can see that, and this, what we just did here was we just subtracted. Subtract 2. So we're giving a fast track here. Subtract 2 from the main diagonal, so that's the express path. So it's just like a shortcut. Okay, so we're subtracting 2 from the main diagonal. Alright, well now looking at this is going to row reduce not to make something like it did before, but we can see that we're going to have a pivot everywhere because these are not linearly dependent on each other. No one row is any kind of scalar multiple of the other, and since there are only 2 of them, that's what it would have taken. So we would see if we went down the path here, we'd get do. So there is no trivial solution. There's no free variable. Which implies that the only solution is the trivial one. So only the trivial solution. Which means no eigenvector, because eigenvectors have to be non-zero, remember. Therefore, so this implies this, which implies this. Therefore, 2 is not. Oops, an eigenvalue. 2 is not an eigenvalue of A. Okay, so that's what it looks like when it is not. So a note, we only look for non-zero eigenvectors. However, eigenvalues are free to be 0 if they want. So eigenvectors this is a note, let's say. Eigenvectors cannot be a 0 vector, but eigenvalues can be any kind of real number. Or, as we'll see later, even complex numbers. But not yet. Let's not worry about that. Okay, now finding eigenvalues is a topic that is a little bit involved, and so we'll save that mostly for another section, but there is one exceptional case where it's relatively easy. So So an easy case of finding lambda, and that is triangular matrices. So remember what I mean by triangular matrices. So that means either upper triangular or lower triangular. So if A is either upper triangular which means all zeros below the main diagonal, or perhaps I should say only zeros below the main diagonal. I'm not saying that every zero in the matrix is there. I'm saying that every entry there is zero. So maybe I'll reword that as only. Only zeros below the main diagonal. Or two, lower triangular, which means only zeros above the main diagonal. Although I guess that's just as ambiguous. So what I'm saying is there are only zeros, in this case below the main diagonal and above the main diagonal. Then, so if A is either of these two things, then the entries along the main diagonal will be the eigenvalues of A. So let's see an example of that, and that'll also explain why this is true. So let's take an example, and we'll make this one a little bit bigger. So an example, find the eigenvalues and associated eigenvectors of the following. And let's make it a 4x4 just to really ramp things up. And we'll make it an upper triangular matrix. So let's go 1, 2, 3, 4, 0, 5, 6, 7, 0, 0. Let's go 0, 8, and then 0, 0, 0, 9. Okay, well, first step of this is very easy. Just go down the main diagonal, and those are your eigenvalues. So lambda equals 1, 5, 0, and 9. And remember, eigenvalues are allowed to be 0. It's only eigenvectors that are kept from equaling the 0 vector. Alright, well now to find the eigenvectors that are associated with each of these, what we'll just do is take them one by one. And that's what you have to do. You have to go one by one on each of these. So if lambda equals 1, then what we're going to have is A minus lambda I. It's going to be this matrix with 1 subtracted off of the main diagonal. So 0, 2, 3, 4. Then we're going to have 0, 4, 6, 7, 0, 0, negative 1, 8, and 0, 0, 0, and 8. Alright. Well, looking at this, we can see pretty easily that we're going to have pivots in all of the columns except for the first column. So the first column is going to be our free variable. And actually, if we were to row reduce this, maybe you're not as comfortable jumping to conclusions as I am, and that would probably be a healthy fear of error. But I can predict with some confidence here what this is going to look like when I row reduce it, and it's going to look like 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and then 0, 0, 0, 0. So if you're not as confident as me, you can go through the steps, or you can use technology to do this row reduction. But we'll notice here that what we've got is only x1 as a free variable. So then if I augment it with zeros, what I'll get and you don't necessarily need to write out cases like this that are kind of by the book, but it doesn't hurt anything on our first spin to make sure that we are dotting our I's and crossing our T's here. So x1 equals x1, x2 equals 0, x3 equals 0, x4 equals 0, which means that x is going to equal 1, 0, 0, 0, and so we just need an example of one of the elements of this family to seal the deal. So we'll have an eigenvector of 1, 0, 0, 0. Okay, so that's 1/4 of the way there. Alright, what about lambda equals 5? Once we've gone through this and we've worked it all out, then we'll take a step back and we'll figure out what was going on there, what we were able to determine in why this even is a recipe for giving us the eigenvalues. So okay, so let's say we got lambda equals 5, so then a minus lambda I is again just going to be a matter of subtracting 5 from the main diagonal. So we're going to have a minus 4, 2, 3, 4. We're going to have a 0, 0, 6, 7. We're going to have 0, 0, minus 5, 8. And then we're going to have 0, 0, 0, and 4. Alright, and then what we're going to want to do here is we're going to want to row reduce. And here you can reason it out kind of like I did there, thinking about where this is going to go. That one obviously is going to be a pivot of 1. Usually I work from left to right on columns, but I could also go the other way, and I could just clear everything up from there, and then I could pivot, and then I could scale that down and pivot everything away up there, and all that's going to be left is over here. But if you don't want to take any flights of fancy, you don't want to take any chances, you can also use technology. So for example, I entered this in, and here's what I got. So you can feel free to make use, copious use even, of technology in some of these. So 1, negative 1/2, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, now I'm going to drop the tedious song and dance of augmenting the zeros and going from there. We know what augmenting the zeros looks like, and we know what the consequences of that are going to be. And so what we're going to end up with here is x1 minus 1/2 x2 equals 0, which means that x1 will equal 1/2 x2. And then as far as x2, that's a free variable here. It's the only one without a pivot, so equals x2, x3 is going to equal 0, x4 is also going to equal 0. So imagine, if you are not as comfortable with acrobatics, that I augmented some zeros and I went through the same process that I've gone through before. So x then will be x2 is the free variable, so that's what's going to be pulled out, and it's going to be a 1/2, a 1, a 0, and a 0. And so that gives us our eigenvector. One half, 1, 0, 0. All right. Now, looking at the next one, that is it's coming down the pike. We've got a lambda equals 0. Now, lambda equals 0 means that a minus lambda I is actually just regular old a. So lambda equals 0 means a minus lambda I is just going to be classic 1, 2, 3, 4, 0, 5, 6, 7, 0, 0, 0, 8, and 0, 0, 0, 9. Alright. Well, if we were to row reduce this, we can see pretty well where our pivots are going to be. They're already actually visible. There, there, and there. And we can see where the free variable is going to be. It's going to be over there. But then as far as the things beyond that, it becomes a little bit harder to tell. And so once again, we can just foist all of the heavy lifting onto the shoulders of calculators, and that's not a problem. And again, appealing to technology, if I wanted to row reduce this, I would get, so as predicted, the free variable is in the third column. The rest are all pivotal, or basic. 1, 0, 3/5, 0, 0, 1, 6/5, 0, 0, 0, 0, 1, and then we've got our obligatory row of zeros. Since this is a square matrix, we had better end up with a row of zeros on the bottom after row reducing. Otherwise, we've done something wrong, because that would imply that we didn't have any free variables, that there were pivots to be found everywhere, which would mean that this was not actually an eigenvalue after all. Alright, so now then let's see what that's going to mean. So that means x1, and I'm just, cutting more and more to the chase here with every step. So minus 3/5 x3, x2, minus 6/5 x3, x3 is just equal to x3, and x4 is equal to 0. So what this means then is that the null space of this matrix is going to look like the things that are parameterized by an x3, and then what we're going to have here is the negative 3/5, negative 6/5. We can have a 1 and we can have a 0. Now, it doesn't really matter to us in this context where all we're doing is reporting an eigenvector, but if you have a situation like this and you think it would be convenient to scale this, you could choose an x3 equals 5 to clear out the denominators if you wanted, and that would be a very common thing to do if it would be useful to do so. For us right now, it doesn't really matter, so we'll just take it as it is. So eigenvector. So what we're reporting here is by no means the only eigenvector. It just happens to be the one where we have we've made x3 equal to 1. But any scalar multiple of this other than 0 will also be a legitimate answer to the same question. So eigenvectors themselves are not unique. They will any scalar multiple of a legitimately found eigenvector will also be a legitimate eigenvector. Alright, so then if lambda equals 9, that's the last one. So you might be able to guess in this case where the free variable is going to be, because these have gone kind of by a pattern. The free variables started off being x1 when we used the first one, x2 when we used the second one, x3 when we used the third one, and now that we're using the fourth one, I think you can probably fill in the pattern there and figure out what's going on. But we'll discuss that in a second. So lambda equals 9, so that means a minus lambda I is going to be regular old a, but we're going to subtract 9 from the main diagonal. So it's going to be a negative 8, 2, 3, 4, 0, negative 3, 6, 7, 0, 0, negative 9, 8, and then 0, 0, 0, 0. So notice we already now we have the row of zeros going into this one. And this time now that I can see where my 3 pivots are, I definitely would rather not go through the tedious arithmetic of reducing it. Not that it would be so hard, but just every brain cell I can spare. And when we appeal to our little electronic genie, we see that we were justified in not necessarily wanting to go through the motions of reducing this ourselves. We can tell by the answer that it was going to be a messy process. So 1, 0, 0, negative 67/36, 0, 1, 0, negative 37/9, 0, 0, 1, negative 8/9, and then 0, 0, 0, 0. Now, once again, if we were in the business of finding the eigenvector here, we would, if we were being very, very careful, we would augment our zeros and proceed accordingly. However, there's no advantage to that because we've been down these sorts of paths so often before that we can predict the answer with some confidence. So x1 minus 67/36 is x4 equals 0, which means x1 equals 67/36 x4, x2 minus 37/9 x4, that equals 0, which implies that x2 is equal to 37/9 x4, x3 minus 8/9, finally a reasonable one, x4 equals 0, that implies that x3 is equal to 8/9 x4, and x4 is equal to x4, which just for completeness we'll say implies x4 is x4, which together then all imply that x is going to be parameterized by the x4, and its entries are going to be 67 36ths, 37 ninths, 8/9, and then 1. Now, if we wanted to make this a nicer thing, we could use the we could use strategic values of x4, such as 36, which is a factor that would clear out the denominator here, here, and here, and that would be nice. However, there's no need to. We're not using this for anything, so there's no reason to be overly cosmetic in the adjustments we make. So the eigenvector here would be 67 36ths, 37 ninths, 8/9, and 1. Alright, so in these big cases of matrices like this one, 4x4, the things, they get a little complicated, and you don't necessarily want to spend too much time trying to shake up what has been our traditional approach to these things. But in the case of a 2x2 matrix, this can often be done in a much quicker way. So note. So as in so many other things, 2x2 is simpler, and we can develop a quicker pathway to victory in this. So in 2x2 cases, we can speed up the process. By just trying to find any vector. And by any, I don't mean any, I mean any non-zero. That fits the bill, and the bill being ax equals lambda x. And let me show you how this can be sped up a little bit. An example here. It would be a equals 1652. And let's say lambda here is -4. So if we really truly have an eigenvalue given to us, then we can make some leaps of faith. So a minus lambda I. So we then subtract lambda from the main diagonal, and what we're going to get is a 5, because 1 minus -4, 6, 5, and 6. And in particular, I don't even need to waste my time row reducing this matrix, because I can see with my naked eye that the bottom row is going to end up being zeros, and there's our basic variable. There's our free variable, and why solve for each one in terms of the other ones when instead the real heart of this is the relationship 5x1 minus 6x2 equals 0. In other words, 5x1 equals 5x1 plus 6x2. I was getting ahead of myself there. So 5x1 equals negative 6x2, which then, if I can just find any two numbers to fit this, that would be a solution. So what could I pick as two numbers to fit this? Well, because of the way it's written, I can see, like if I put in a negative 6 for x1 and I put in a 5 for x2, those are going to just be two copies of the same thing. So you can just kind of like swap the coefficients. And you can get x1 equals negative 6, x2 is equal to 5. This would be an example of a vector, or two values, x1 and x2 anyway, that would satisfy this, which means then an eigenvector this is just one of a whole infinite family of eigenvectors I could have chosen, but any other one would just be a scalar multiple of this, and it'll be like this. Now, the reason why this works so well in a 2 by 2 case specifically is that when you have only two rows and you really have an eigenvalue, then you can immediately see that that this is going to cancel out that one. There's not going to be any funny business. There's not going to be any fancy amount of which variables are free and which ones are basic. It's all going to be very stereotyped, and you can cut to the chase quite a bit quicker. And because finding eigenvectors is going to be such a valuable skill for us, particularly in Math 256, we would want to be able to have access to the finest and smoothest techniques and shortcuts available. Okay. So that's that. Now, eigenvector, eigenvalue, that's all well and good. But we can actually put eigen in front of other things, and actually in for example physics, people sometimes say eigenfunction, there's eigen this, eigen that. But what we can also do is eigenspace. So note, for each eigenvalue, the collection of linearly independent associated eigenvectors will form a vector space, which will be a subspace of Rn. And we'll call that the eigenspace. The eigenspace of A associated with lambda, or corresponding to lambda. So then finding a basis for the null space of A minus lambda I we'll be finding the eigenspace, finding a basis for the eigenspace. finding a basis for the eigenspace. The eigenspace of A corresponding or associated with, so corresponding to lambda. Okay, so that's our recipe for finding the basis of an eigenspace. It is to just do what we would do to find the basis of a null space. So, if you remember how that goes, that's a process that's very similar to what we just did before. The catch is here that we can have multiple different eigenvalues, or sorry, multiple different eigenvectors that are linearly independent of each other, all corresponding to the same eigenspace, or all same eigenvalue. So as an example, let's take A is equal to, and now let's go with 1, 2, 2, 0, 3, 0, and then 0, 0, 3. So we can see actually the two different eigenvalues of this because this is upper triangular, and so we know that the eigenvalues are 1 and 3, and in particular, let's say that we want to find the eigenspace for A corresponding to lambda equals 3. So what makes 3 special in this case is the fact that there are 2 copies of it along the main diagonal, which means that it is what is called a repeated eigenvalue. We'll explore a little bit more what that means in a later section, but for now, just take it given to us and work with what we have. All right, well, let's see what we get here. So A minus lambda I means take A and subtract 3 from the main diagonal. So we get minus 2, and then 2, 2, 0, 0, 0, 0, 0, 0. Well, we can immediately see what's going on here. This is going to be 1, negative 1, negative 1, 0, 0, 0, 0, 0, 0. And what this means is what we've got are 2 different free variables, x2 and x3, which means the dimension of the eigenspace here is going to be more than just 1, it's going to be 2. So thinking about this, x1 minus x2 minus x3 equals 0, which means that x1 equals x2 plus x3. x2 obviously just equals x2, it's free. x3 just equals x3, it's free. And then what this means is that any x that is going to be a member of this null space is going to be of the form x2 times 1, 1, 0 plus x3 which is going to be 1, 0, 1. So then, the basis for the eigenspace would be these 1, 1, 0, 1, 0, 1, and because there are only 2 of them, we can easily see that they are linearly independent of each other, because for 2 vectors to be linearly independent just means not to be a scalar multiple, and that's clearly the case. So then the eigenspace the eigenspace of A corresponding to lambda equals 3 is going to be the span of these. So this was a basis, so therefore the space is what is spanned by them. Now, just for the record, suppose we repeat with lambda equals 1. So the other eigenvalue here. So let's see what's different about this one. So the other eigenvalue in this case is just lambda equals 1, because again this was a triangular matrix. We'll find out in the next section how to find general eigenvalues. But for now, the only ones that we can actually find by any systematic means are for diagonal matrices. Otherwise, you'll have to be given the eigenvalues in this section. Next section, though, we'll pull ourselves up by the bootstraps and figure out how to find the eigenvalues for ourselves. So repeat now for lambda equals 1. Okay, so now what if we do a minus lambda I, where lambda is going to equal 1? Well, what that's going to give us is 0, 2, 2, 0, 3, 0, sorry, 0, 2, 0, and 0, 0, 2. Not that it really actually is going to make any difference in the long run, because we can see what's going to happen here. We're going to be able to just move that up there, scale it down, clear everything, and we can see how this is going to shake out. We're going to get 0, 1, 0, 0, 0, 1, 0, 0, 0, which means that x1 is going to be free, x2 is going to be 0, x3 is going to be 0. Since those ones didn't have any dependence on x1 and they're basic, they're just going to be values. And so then the x now is going to be x1 times 1, 0, 0, which means that our basis only has one element in it and that the eigenspace is only going to be one-dimensional. So here's our basis. And then that means that the eigenspace itself is going to be the span of that. All right. So now we'll finish this section off by just stating a theorem. It's an interesting theorem, but it's not something we're going to prove or anything. This is not a proof-based class. At its heart, it is fundamentally a place to learn how to find and calculate certain things. So we'll just state it and accept it as a fact. So theorem. The eigenvectors associated with different eigenvalues are linearly independent of each other. So what that means is that basically the eigenspaces, in a way, are they're going in different directions. They don't have any elements in common other than the zero vector. So 0 is permanent party in all vector spaces, so they're obligated to accept it. However, any other vector that belongs to one eigenspace is therefore not part of another eigenspace. So this means the eigenspaces of distinct eigenvalues share only the zero vector. They have no other vectors in common. Now, if you want to know, so I can tell you actually a sketch of how the proof of this would go. If you want to know how this is proved, suppose you did have different eigenvalues for a bunch of different eigenvectors. So each one had its own eigenvalue. Then, if you were to suppose that some combination of these eigenvalues, or sorry, eigenvectors, were to equal 0, then that's what it would mean to be linearly dependent. Now you can apply the matrix A to this relation, and what you'll get is A times a bunch of vectors added together with different combinations equals the zero vector. But then each of those vectors in turn gets multiplied by its corresponding eigenvalue, and then what that means is you can actually effectively set up an equation, cancel away the first term, and what you end up with is a smaller relation of the eigenvectors that end up equaling 0. Now you can't keep that process going on forever, and so by the principle of mathematical induction, what that means is that basically it would have had to bottom out at some point, and so that means that actually it couldn't have ever gotten started. And so what that means is that the linear combination equaling 0 was an impossibility from the very start. So again, I didn't write down any of that, and neither are you obligated to write down any of that because it's a little bit tricky reasoning. But the basic idea is it's more or less like a proof by contradiction or a proof by induction. And what happens is it just it says, well, what if this were false? And then it shows that it couldn't have ever happened. There was no first time for it to be false. Anyway, so that's enough about that. And that's enough for section 5.1, so join me for the next episode of Math 261, where we will discuss section 5.2, the characteristic equation. Alright, till then, bye!